right? So alkenes, if you remember from earlier when we talked about functional groups, right? An alkene is just some compound that contains a double bond, right? Somewhere in there, right? So when you talk about alkenes are really flexible and really what's the word I'm looking for? Versatile, very versatile. It's a very versatile functional group because you can, the section that we're talking about now, we're going to be talking about how they react, right? And how to convert them into different compounds, right? So if we take an alkene and let's just say we treat this alkene with HCl. I'm not going into the mechanism or any of that stuff because we're going to talk about that plenty, all right? But if I treat it with HCl, right? This and let me say this: alkene reactions are all additions, right? We talked about substitution, rearrangement, elimination, and addition as the four main reaction types. So every time you take an alkene and you do a reaction on it, it's going to be an addition reaction, right? So with this alkene, if I add HCl to it, what ends up happening, and this is another key element to alkene reactions, is that you add something to each side of that alkene or each carbon in the alkene. So in this case, let me do this. Right? Come on, AT&T, stop playing with me. All right. So we have we're going to add this across here. I'm not going to talk about the mechanism, but what ends up happening is my alkene now gets converted into an alkyl halide. So now the chlorine is here. The hydrogen is here. Right. And so that's one of the ways that we can take an alkene and turn it into something else. Right now, we're going to talk about several different types of reactions, and they're going to be classified, right? As we can kind of group them into what type of functional groups we're converting the alkene to. So we're going to talk about alkenes getting converted into alcohols. Right, we're going to talk about alkenes getting converted, and this is an alkyl halide. We're going to talk about alkenes getting converted into carbonyls. Right, there are certain specific sets of reagents that'll take an alkene and turn it into a carbonyl. Right, we'll also talk about how to turn alkenes into epoxides. And again, if you learn these reactions now, you will it is going to benefit you when you get to part two. I can't tell you how much time I spend in part two reviewing reactions that were learned in part one that are like basic reactions now, not anything esoteric or out there, like basic stuff like how to do how to convert an alkene into alkyl halide. I spend a lot of time having to review that type of stuff, right? So alcohols, alkyl halides, carbonyls, epoxides. Right, that's one of the reactions that we're going to learn. We're going to learn how to convert them into cyclopropanes. And I know this sounds like a lot, but I promise you it's not as bad as it looks. And also, what other, there's one other reaction. Oh, alkanes. right? So how to take that double bond and reduce it down to nothing, right? Until it becomes a single bond, right? And there's a way to do that. Every one of these um, reactions has a set of reagents. Let me erase this so I can make this look better. Every one of these reactions has a set of reagents that allows for this transformation. So like if I want to convert this into an epoxide, I can use hydrogen peroxide, right? That's one way to do it. If I want to turn it into a cyclopropane, I use zinc and diiodomethane. If I want to turn it to an alkane, I just need to add hydrogen gas to it, right? And in the presence of a catalyst, right? Some type of catalyst, palladium, platinum. It depends on what type of hydrogenation you're trying to do. Go ahead, Tia.
Can you scroll over to the left? Okay.
So like, and if I want to convert to a carbonyl, one of the ways that I can do that is with ozone, right? I can use ozone and convert it into a carbonyl, right? If I want to convert to an alkyl halide, you see the reagent right here. I can just use HCl. If I want to turn it into an alcohol, there are a lot of different ways to do that. But one of the main ways is to use a process called hydroboration. So BH3 followed by hydrogen peroxide. That's one way. There's another way using mercury.
I have a question.
Go ahead.
What does the first one say?
First
The reagent.
reagent up here.
No, under alcohol.
Oh, it's BH3.
Is that then the word?
Mm-hmm.
Oh.
It's a two-step process.
Okay.
Yeah, and then the second one is mercury acetate. Right, so mercury acetate and then water. And those are, again, if you commit the reagents to memory, then the reactions don't become so daunting because all of these things have rules that go along with them, right? For epoxidation, there's a rule. There's a rule that the double bond has to be cis. It can't. The epoxide is always going to be cis. It'll never be trans, right? For alkanes, it's, if you take the catalyst and hydrogen gas, you're always going to get out an alkane. The double bond is always going to get reduced. For alkyl halides, it's regiochemistry. Which carbon is the chlorine going to? Which carbon is the hydrogen going to? All those are rules that we'll learn. And if you commit the reagents to memory, then the other parts of the reaction, they'll stick to, right? And that's what I'm telling you to make flashcards, put the reaction on the front, on the back, put the characteristics. Oh, and you don't know this term yet, but I'm just saying it's Markovnikov or anti-Markovnikov, or it's cis or it's trans or whatever. If you learn though, if you put that on the back, put the reaction on the front, as we walk through these mechanisms and the arrow pushing, I promise you it's gonna stick, but it's gonna take some work on your part. You can't sleepwalk through this section because it's a lot. So let me talk about some other characteristics of alkenes, because the reactions part, I just want to introduce you to that. But there are other things that we're going to talk about, like other basic things like Alkenes Stereochemistry.
Wait, did you say to like put the reagent on the front and the reaction on the back? What did you say to put on the flashcards?
No, the reaction, like write out the react. I'll show you. I'll give you an example.
Okay.
You'll write my suggestion is to put the reaction on the front, and then on the back, of the flashcard put the characteristics,
Okay.
whether it's Markovnikov, anti-Markovnikov, whether it's cis, trans, um, whether it's that's one something else. I just it slipped in my mind. It's Monday. But yeah, the characteristics of the reaction will go on the back, right? Whether it's low temperature, high temperature, so on and so forth, like that. But when we get to the reactions and start talking about them and start talking about the different characteristics of those reactions, you'll understand more what I'm talking about. So let's talk about alkene stereochemistry. And all it when you hear that term stereochemistry, it's just the 3D orientation of the alkene. Right. So a basic alkene would look like this. And we talked about this already, right? This has no substituents. Right. And then you can have monosubstituted. And so on and so forth, mono, di, tri, tetra, right? But only when you have only if you have a disubstituted alkene, something like this, do you get into worrying about the stereochemistry, right? So this is disubstituted. And this particular orientation, where both of your groups are on the same side, right? We call that the cis orientation. So this is cis. It just means the two groups are on the same side. And it has to be disubstituted in order to be cis or trans. All right. And if you have an alkene like this, same alkene, but notice stereochemistry is different, right? The two groups are not on the same side, they're now on opposite sides. Right? This is what we call a trans alkene. It's a trans alkene. So yeah, cis and trans. The thing about it is with these cis and trans alkenes, they have different physical properties. So they're going to have different boiling points, different melting points. They're going to, the solubility will be different, all of that, right? And one of the things, the times you probably heard the term trans is when you're talking about trans fats, right? Trans fatty acids and how bad they are for you. And the reason they're so bad for you is because the trans, if it's a trans fatty acid, the geometry of that double bond allows those fatty acids to pack better. So when they pack better, that means they accumulate more. When they accumulate more, that means they clog your arteries, as opposed to having, a cis double bond in the chain. So trans fatty acids, the reason they're bad for you is because that trans geometry allows them to stack and pack much better, right? So if it's monosubstituted, there's no stereochemistry. You can have cis or trans, or if it's disubstituted, you can have a situation like this where both groups are on the same carbon and it's neither cis nor trans, and we just call this a 1,1 disubstituted system. Right, so that can't be cis or trans because both groups are on the same carbon. All right. And then you can have with trisubstituted alkenes, you have to use a different convention. So let me talk about that for 1 second. And then we're going to get down here to some of these examples. So for trisubstituted alkenes, right? If I have a carbon double bond and I have three substituents on it, right? Right? When you have a tri-substituted alkene like this, you don't use cis or trans to describe it. You use another nomenclature, another type of nomenclature. You use what we call E and Z. So E is, let me make sure I spell this right. So it's E is kind of a short for what we call Entgegen, German term. It just means opposite, and I'll explain that in a minute. And then Z is zusammen, which means same. All right. So that makes no sense right now, but it will in a second. So with a tri-substituted alkene, first what we have to do is look at each side separately. Right? So we're going to look at each carbon in that alkene as a separate entity. And what we have to do is prioritize the groups on each carbon. So over here, you got a oxygen. We're not worried about the hydrogen because we're only looking at the atom that's bonded to the carbon. And you have a hydrogen. So the priority is based on the atomic number, right? So oxygen has an atomic number of 16. Uh-oh. Right, and then hydrogen has an atomic number of 1, right? Right, so on this carbon, the high priority group is oxygen. So this is right. So you're basing that on the atomic number. So the high priority group is oxygen. On this carbon, on the other side, what we're looking at is carbon, which is here, and bromine. Sometimes there's a temptation to try to add up the numbers. Don't do that. Just look at the atom that's directly attached to carbon. So bromine has an atomic number of 79. And then carbon has an atomic number of 12, right? So which one is higher?
Bromine.
Bromine, right? So your high priority group is here.
I have a question.
Go ahead.
Why are we looking for the high priority group again?
Because we need to figure out whether it's E or Z. Because it's a tri-substituted alkene, and so you can't use cis or trans if it's tri-substituted. So you got to use a different convention. And so we use E or Z. So now we go back to opposite versus same. So in this case, the high priority groups, are they on the same side or are they on opposite sides?
Opposite.
They're opposite. So this is an example of what we call an E alkene. What that means is that my high priority, let me see if I can zoom in because I got to fit this in here. My high priority groups are opposite. Right? I can take that same alkene and put the OHs group here and leave the BR here. And now the high priority groups on the same side. We already prioritized it in the first example. Right? So if that's the case, then this is a Z alkene, right? Your high priority groups on the same side.
How are they on the same side? Because I thought you drew the line down the middle, so they're still on different sides.
Not on the same carbon, on the same, let's say in the same plane,
Okay,
right?
thank you.
Yeah, so it's not on the same carbon. What I mean, they're on the same side of the double bond. So you have a top side and a bottom side.
Sure.
Hold up.
I have a question.
Go ahead.
Um, so the line, the red dotted line that you
Mhm.
drew at the top, so what is that for?
Okay, so if it's a trisubstituted alkene, we have to look at each carbon in the double bond separately. So, I put that line there to indicate that the carbon on the left and the
Mhm.
carbon on the right, you have to look at separately in order to determine if it's E or Z.
But so when the Z alkene, those are on the same side. They looks like opposite sides.
Okay, so think same side. Think about this alkene being flat, planar, right? So if this is a plane like this, if I have groups here, they're on the same side of that plane.
Mhm.
And if I have groups here, then they're on opposite sides of that plane. So not on the same carbon or the same side of the alkene, but the same side of the plane.
Okay.
I have a question as well.
Go ahead.
For it to be tri-substituted, I remember us drawing like CH3s. You can, I guess, replace those CH3s with any other
Yes.
this type of.
Any other atom, but other than hydrogen.
Okay.
Mhm.
And then my other question was, did you put Z equals 16? What does that Z stand for?
The atomic number.
Okay.
Yeah, so that's how you prioritize based on the atomic number. I should have written that in. Let me see. I got room. I'm gonna move this down and write that in.
So the Z can stand for both the atomic number or one of the like the E or the Z. It can stand for either one.
Mhm.
Okay.
Right. So the priority, you base that on the atomic number. And you only do this with tri-substituted or tetrasubstituted alkenes. Because you have the same convention. So if you got a tetrasubstituted alkene, there's no cis or trans, it's going to be E or Z. And again, E means that your high priority groups are opposite to one another. And Z means your high priority groups are on the same side of the plane as one another.
Okay, so you said tribe, you don't have any cis or trans, or
No,
do you?
no. You have to use E and Z. You only use cis or trans when you're dealing with disubstituted alkenes.
Okay,
Right. So you can see with the cis is the two CH3 groups are on the same side of the plane, right? And then with the trans, they're on opposite sides of the plane. Back to you.
Yeah. So why can't we use cis or trans? Because to me, it looks like we're doing the same thing.
Yeah, you're kind of doing the same thing, but the convention is different because you have more substituents. And so when you get into 3 or 4 groups attached to that double bond, then you just have to use a different type of nomenclature. Right? If it's more than 2 groups attached, then the convention is to use E and Z and not cis and trans. And again, this is why nomenclature is my least favorite topic, because there's like a million different rules that you have to follow. But and all that's based on I don't know if y'all, well, you probably haven't because I haven't talked about it. But it's like all of these are what we call IUPAC rules, the International Union of Pure and Applied Chemists. So then all the nomenclature rules are based on IU convention. So the E and Z for tri tetrasubstituted alkenes, that's an IUPAC rule. Same as cis and trans. All of that is a part of the IUPAC convention for nomenclature on different compounds. But this is why I hate nomenclature. It's my least favorite topic of all topics in organic. I'd rather eat nails with hot sauce than talk about nomenclature. But I had to introduce it because you're going to see it and you're going to hear the terms. So it's the same thing, but you just use a different you use a different convention to determine the same thing that we just looked at, like whether something is opposite or same side. You just use a different convention. All right. Other questions? Any other questions? Man, it's 10:41. All right. Another topic dealing with alkenes is the topic of degrees of unsaturation. Right. So let me cut this and then actually I'll cut them both out, but I'm gonna paste them separately because I want to talk about each one separately. I need to add a page. So let's talk about degrees of unsaturation first. Okay, no, let's do this. Let's go back and name these. Let's do that. That'll be that'll be better because we've already talked about cis and trans and all that. So let's stay in that vein, and then we'll do degrees of unsaturation Wednesday if we have, or we have time to do it today. We'll do it today. All right, so let's start with this one. All right, because you kind of have an idea about naming because we kind of did a little bit of it before. And so what's the first thing you have to do? Anybody remember?
you're talking about writing the priorities?
No, we're not
You gotta count the carbons.
count the carbons, find the longest chain. And if it's an alkene, the longest chain has to contain the alkene, right? It can't be a chain that doesn't contain that functional group. So in this case, we counted, well, I was just putting the dots in while y'all were thinking, while the wheels were turning, was 1, 2, 3, 4, 5, 6, 7, 8 carbons in that chain. If we were to count a different way. 1, 2, 3, 4, 5, 6, 7. There's 7 carbons in that chain, right? If you start it up top, because I know like these are things that y'all are thinking about. Why can't we start here? If we count here, 1, 2, 3, 4, 5, 6. Am I right? Oh, look, that's the same carbon. 6, 7, 8. That's 8 carbons too. So that either if you count it that way, it wouldn't matter. If you started at this terminal carbon right here or right here, it would make a difference. But the other chain is shorter, right? The other chain is 7 carbons. So we're gonna keep the pink chain that I already have on here. All right. Because that's 8 carbons. And now the other part is which end do we start counting from? So anytime you have a chain, you want to count from the end. In the case of alkene, you want to start from the end closest to that functional group, right? You don't want to start counting down here because that's going to give the functional group a higher number than it should have, right? You want to always give that alkene the lowest number possible. So we're going to start counting from that end. So this is going to be 1. That's 2, 3, 4, 5, 6, 7, 8. We don't want to count the other way because then where 2 is, that'll be 7. And if you can give that alkene a lower number, that's what you want to do. So you always want to count from that end first, where you first encounter the alkene, the closest end to the alkene. All right. Write that in here. So you want to start counting from the end as closest to the alkene. And how many carbons do we have again?
8.
8.
8. So 8 carbons. What's the parent going to be?
Octane.
Oh,
Octane.
Something, right? Okay, great. So now I'm going to write this down here because I don't want to try to squeeze all that in there. So the parent, that's why you always find the longest chain, because the parent actually matters, right? We want to find the parent compound. So the parent compound is going to be oct something. But the fact that there's an alkene present, we got to change the suffix to -ene, right? -ene means that there's an alkane present. So octene is my parent. And then if you notice the alkene is located between 2 and 3, is that right?
Yes.
All right, so the address for the alkene we're going to put with the parent, and we're going to give it the number 2 because that's the lowest number. So if it's between 2 and 3, you give it 2. So you say 2-octene. If it was between 3 and 4, you say 3-octene. If it was between 4 and 5, you would say 4-octene, so on and so forth. So you want to give the alkene the lowest number possible. Right? Lowest number possible. All right. Any questions about that so far? So now what if we look at that longest chain, what is this group right here? Because it's not in the chain, is it?
Is it a,
no.
No. So it's what do we call it if it's not in the chain? We also got a group right here too.
is it a methyl?
Yeah, it's a methyl, but what's the generic name for something that's attached to the chain or
What's-
attached to a ring?
Substituent?
It's a substituent. Very good. Right. So this is a methyl. And this is 2 carbons right here. Y'all see that? That's attached to that chain. So it's a ethyl. That's CH2, CH3. We're good so far?
No,
Yeah.
can you,
Can you
Oh.
explain that again?
The 2
Yeah.
carbons. So if, let me, I got a couple of minutes left. So methyl is from this group, right? Which is CH4. But if I take off one of the hydrogens and attach it to something else, it becomes CH3. So that's why we call it a methyl. The same with ethane. That is CH3. It's a 2 carbon chain. But if I attach it, I have to take one of those hydrogens off so I can attach it. So then it becomes CH2, CH3, and I just changed the suffix to ethyl. Right, and you can see up here that this group right here is 2 carbons. Is that right?
Yes.
Yeah, because we're not counting this carbon because that's part of the longest chain, right? That's one of the carbons in my chain. So it's not a 3 carbon chain that's attached to that longest chain. It's a 2 carbon chain.
please go down or zoom out, please.
So all of your substituents, your alkyl substituents, are going to be based on whatever their name is as an alkane. So if it's ethane, it's going to be ethyl. If it's propane, which is 3 carbons, if it's a substituent, it'll be propyl. If it's butane, if it's a substituent, it'll be butyl, so on and so forth. All right. So we got the parent 2-octene. We got our 2 substituents, methyl and ethyl. And where are they located?
Methyl is
Where's the
located
methyl?
on 2 carbon.
Say that again.
Methyl's located on the 2nd carbon.
So 2 methyl. And then what's the ethyl? Where's that? Carbon 5. Is that right?
Yes.
Right. So we got the basic part of our name down. We got 2 methyl, we got 5 ethyl, and we got 2-octene. And then what are we missing? Are we missing anything? The fact that that alkene has 2 methyl groups on it, you see right here. We're not going to be able to assign it's trisubstituted, but we can't assign priority because both of those groups on that carbon are the same. So we don't have to include the stereochemistry. So we're just going to write the name out. What's going to come first, ethyl or methyl?
Methyl.
It's alphabetical, remember. It's not based on the number. So it's alphabetical. So it's going to be 5 ethyl. Notice I'm capitalizing that first letter. That's a IUPAC convention. 2 methyl. Is that right? 2-octene. That's the name of that compound. Go ahead.
So the parent always comes last.
Yes.
Hmm.
Anytime you're naming a compound, the parent is the last part of the name. So you have parent, which is the street. And then the substituents are the residents on the street. And then the numbers where the substituents are located, that's their address.
How do you know that it's tri-substituted? I don't see that.
Look, if you look at the double bond itself, it's got a carbon here, a carbon here, and a carbon on that side.
Okay, and you said that it has no
No stereochemistry, because if it can't be E or Z if you have two groups that are identical. So you see how over here where I have that purple line right here, those two carbons are the same. So I can't prioritize them. If they both got the same atomic number, then I can't prioritize them. Because that's what I base the priority on. If it's tri-substituted, it's going to be E or Z. But I can't prioritize the groups on that side of the double bond because they're both the same. So I just leave the stereochemistry out.
Are you talking about on the same side of the double line?
Yeah, the two pink carbons I have highlighted right here. You see, both of those are CH3s here and here. So I wouldn't be able to prioritize that side.
Okay.
All right, we got to stop. We're 5 minutes over. We'll pick this up on Wednesday. We'll do a couple of more nomenclature examples, and then we'll do index of hydrogen deficiency or degrees of unsaturation. And then we're going to jump into these reactions. We'll probably start doing the reactions on Friday, maybe Wednesday, because I don't want to spend a lot of time on nomenclature because it's just it's boring and it's taken away from the more exciting stuff. Not saying it's not